Section: Introduction. In this section, we will discuss the transformer, which is a widely used neural network architecture for processing sequential data. The transformer takes a sequence of raw data vectors and converts them into a more informative representation. This new representation needs to capture both the order of the items in the sequence and the relationships between them. To achieve this, the transformer algorithm includes two key steps: positional encoding and self-attention. Positional encoding adds information about the order of the items to the raw data representation, while self-attention helps ensure that related items have similar representation vectors. Many variations of positional encoding have been proposed, such as relative positional encoding and introducing learnable parameters to the encoding vector. While these approaches have shown promising results, they are often evaluated on specific datasets, which may limit their generalizability. To address this limitation, we introduce a new concept called faithfulness in positional encoding. We aim to create a positional encoding method that faithfully represents the position information in a principled way. Our approach, called DFT encoding, leverages the discrete Fourier transform to achieve this goal. By ensuring faithfulness in positional encoding, we have improved the performance of the classification task. Our work is the first to derive an optimal positional encoding method based on the principle of faithfulness. In summary, the transformer algorithm aims to enhance the representation of input sequences by capturing both the individual item information and the relationships between items. Our proposed DFT encoding method ensures faithfulness in positional encoding, leading to improved performance in classification tasks. Section Summary. In this section, we introduce the transformer algorithm, a powerful neural network architecture for processing sequential data. The transformer converts raw data representation vectors into more informative ones by incorporating positional encoding and self-attention mechanisms to capture both the order and interdependency of items in a sequence. To address the arbitrary nature of positional encoding, we propose a new method called DFT encoding, derived from the theory of discrete Fourier transform, which ensures faithfulness and improves classification task performance. This work represents the first attempt to derive an optimal positional encoding based on the principle of faithfulness. Section: The transformer algorithm. In this section, we will explain the transformer algorithm. The transformer algorithm consists of two main steps: positional encoding, PE, and self-attention filtering. For positional encoding, the aim is to incorporate the position information of items, e.g., words in machine translation, in the input sequence. Initially, an extra vector is added to the raw representation vector of an input word to achieve this. The specific sinusoidal form used in the original formulation was chosen based on the intuition to capture various length scales of word-word dependency. Moving on to self-attention filtering, after applying EQ, we update the data matrix to get a new matrix. This self-attention filtering process involves three key steps. Firstly, three different feature vectors, query, key, and value, are created from the data matrix. These feature vectors are obtained using matrices that are to be learned from the data. Secondly, a self-attention matrix is computed from the query and key matrices. This matrix essentially represents the similarity between different items in the sequence. Finally, the influence of neighboring items is considered in each row to encourage similar values among representation vectors. Moreover, the transformer algorithm deals with finding representation vectors for items in a sequence. This process can be likened to assigning a function on a one-dimensional lattice with a specific number of lattice points. The discrete Fourier transform, DFT, plays a crucial role in this context. The DFT allows us to expand any function defined on a one-dimensional lattice with a specific number of points into a set of coefficients, providing a mapping from the function to these coefficients. The orthogonality of the Fourier bases simplifies finding these coefficients, making the DFT an invertible transformation. Section Summary. In this section, we delve into the transformer algorithm, which comprises two key components: positional encoding, PE, and self-attention filtering. PE aims to incorporate positional information of items in the input sequence by adding a sinusoidal positional encoding vector to the raw representation vector of each item. Self-attention filtering involves creating query, key, and value feature vectors from the data matrix, computing a self-attention matrix to capture item relationships, and encouraging representation vectors to align with their neighbors, often implemented using multiple heads for enhanced performance. Section: Fourier analysis of positional encoding. In this section, we will discuss how Fourier analysis is utilized to assess the effectiveness of positional encoding. The original positional encoding, PE, exhibits a strong low-pass characteristic. PE involves determining a representation vector of an item in an input sequence of length s in d dimensions. Initially, the position of an item in the input sequence is represented by an s-dimensional, 1-hot, vector, where only one entry is 1 and the rest are 0. However, this representation is not ideal as it lacks continuity and makes numerical optimization challenging. The original PE aims to overcome these limitations. To evaluate the effectiveness of the original PE's specific functional form, one suggested approach is to use discrete Fourier transform, DFT. By applying DFT on a one-dimensional lattice with d lattice points, any function can be expressed as a combination of sinusoidal functions with frequencies omega_k. The distribution of these frequencies in the Fourier space is skewed towards 0 due to the power function used in the original PE. The skewed distribution of frequencies in the original PE suppresses mid and high frequencies, leading to a focus on global long-range dependencies rather than short-range differences in location. This can be problematic in applications where short-range dependencies are crucial, such as in time series classification for physical sensor data. Furthermore, an experiment was conducted to understand the impact of the skewed frequency distribution on a reference function. The reconstruction results showed that the original PE failed to accurately reproduce the reference function, indicating a lack of sensitivity to differences in location up to a certain range within the sequence. To address the faithfulness issue, a new positional encoding method called DFT encoding is proposed. By leveraging DFT representation as a smooth surrogate for the one-hot function, the DFT encoding ensures faithfulness by providing an accurate vector representation of the one-hot function. The DFT encoding is proven to be faithful due to the properties of DFT and the existence of an inverse transformation. Unlike the original PE, the DFT encoding does not exhibit bias towards specific Fourier components, as shown by the flat distribution in the Fourier domain. The reconstruction experiment demonstrated that the DFT encoding successfully reproduces the location functions, highlighting its effectiveness in faithfully representing positional information. Section Summary. In this section, we discuss how Fourier analysis is utilized to assess the effectiveness of positional encoding. The original positional encoding exhibits a strong low-pass property, aiming to address limitations in representing item positions in input sequences. By leveraging discrete Fourier transform, DFT, for positional encoding, we introduce a faithful encoding method that accurately captures positional information without bias towards specific frequency components, unlike the original positional encoding. Section: Experimental Evaluation. In this section, we evaluated DFT-PE by applying it to a time series classification task. Our input consisted of multivariate time series, and the goal was to determine if the input time series was anomalous or not, represented by a binary label. We conducted our experiments using 3 benchmark datasets: Elevator, SMD, and MSL. The outcomes are presented in a table, with F1 score indicating the balance between precision and recall. For further information on the experimental assessment, please refer to our related paper.